Webcast Wednesday. I'm Dhruv Choksi, I'm an applications engineer, and I'll be taking you through an introduction to control design in LabVIEW. So just when we start, I want to talk about the various areas in which control systems are typically used. Most commonly, you'll notice that there is a temperature control for the water in your shower in your own bathroom. Besides that, there are a wide range of applications in industry as well. Let's consider an oil refinery. There is process control to continually manufacture and produce oil. Sometimes control systems are also part of the end product, like in the automotive industry and in F-16 fighter jets. Also, in industries where you need precision machine control, like manufacturing and engineering research, control systems are present here as well. And another field of application is motion control, where you need precise control over motors and the signals you send to them, which in turn control the position of cameras and other machines. So, talking about control systems design process. If we break it up into the basics, there are basically 5 stages of this design process. The first and most important one is modeling. The aim of this stage is to create an as accurate as possible mathematical representation of the system. The aim is also to know how the system behaves and to represent this. And this can be done in various ways, such as going to the first principles and writing out the spring mass equations and getting up to the model from there. A lot of assumptions are also made at this stage, so these need to be factored in so that you come up with an accurate model. The next stage is the control design stage. Here, the aim is to actually do such a thing by virtue of which your system behaves exactly the way in which you want it to behave. If you, for example, are using a car and you want to brake, the brake should actually be applied when you press the lever. So there should not be a delay. This is what I mean here. So there are many tools to do this as well, and in the following half an hour, I'm going to show you how to do this graphically in LabVIEW. The next stage is the simulation stage. Here, the controller as well as the system are made to work together in a simulated environment. Here we do a point-by-point approach and we use solvers to get our simulation in tandem. Here we also need to do things such as manage the system timing and also look for loopholes in our system so that we can use this information to improve in the next stage, which is the verification stage. Here we also add non-linearities and make our system capable of responding the way we want in the real world with non-linearities. And finally, we come to the deployment stage. This is where we transfer our control system onto hardware and actually deploy it. Now that we've already got these stages in order and assuming that we know how to model our system, now we have to transfer this information into an understandable and computable piece of information in LabVIEW. So this is where model construction comes in. And there are 6 different ways mainly to represent your models in LabVIEW. I'll quickly go through them. You have the transfer function model, the state space model, the pole zero model, the math script model, M files, you have the PID controller model and the interactive design model. Now once you have your model constructed, you need to find out what it's behaving like. So that's why we look at the time response. Typical things that we look at would be the step response, the impulse response, the rise time, the peak time and the overshoot. Now once we know the time response, we also want to look at how the frequency response looks in terms of the Bode plot, the Nyquist plot, the root locus and the pole zero map. So now that we have these things established, I'm going to take you into LabVIEW and show you how this is actually done on a VI. So this is basically my blank VI which I open up, and my front panel and my standard block diagram are right here. Now I'm going to start with the modeling. So this here, what you see on the left bottom is the control design palette. This is where all my functionality is present and I can choose to use whatever I want. I'm going to start with the model construction. Let me just take a simple transfer function model and show you how we can build a control system in this representation. So I'm just going to drop it onto my block diagram and I'm going to create a control for my numerator, and similarly I'm going to create a control for my denominator. This enables me to directly feed in the coefficients of the polynomials for both the numerator and the denominator, which in turn define my control system transfer function. Now once I have the transfer function here, I use a VI called the CD draw transfer function equation. This will enable me to actually view my equation on the front panel. So I'm just going to connect this here and I'll create an indicator here so that I can see what my equation looks like. Now all I have to do is just fill in the values. So I'm just going to fill in some values here. I'm going to simply run my program. And you see it's as easy as that. You just fill in the values and your equation pops up right there on your front panel. So this is the most basic and the simplest way to represent your system. Now another way to do this is through the state space method or the state space model. So what happens here is that you have 4 matrices and the entire system is represented through the values or the elements of these 4 matrices. So I'm going to show you how that is done. So this will create my state space representation for the system, and I just have to fill in the A, B, C and D matrices. So I'm just going to create controls for them, for all 4 of them. And again I need to draw this transfer function in order for me to be able to show it on the front panel. So I'm going to use this VI here, connect it, and add a simple indicator here. Now once I fill in the values for my 4 matrices, my state equations will come up here. But before that, I want to show you another speciality, which is using the math script node to convert representations as well as to obtain the transfer function. So if you just go into the structures palette and go to the math script node and draw a simple box here, I'm going to create 2 inputs to this, one for my numerator for my transfer function and similarly one for my denominator. I'm just going to connect the numerator to the numerator control I already have here, and similarly the denominator to the denominator control I already have here. I'm just going to type in some script. If you have some .m files, this is where you put them in. So first I'm going to create a variable called df, which will have my transfer function. And next I'm going to create a variable called ss, which will represent my state space model. So this is a function which will basically convert one model into the other. I'm going to create an output for my state space model as well as for my transfer function, and I'll create indicators for both. So just to make it a little better visible, I'm going to move this to the left here, and I'm just going to run this. And as you see, here is the transfer function indicator, which basically shows us the numerator and the denominator, which is precisely the same as what I had filled in earlier. So that's how I've got my transfer function using the math script node. And similarly, this indicator here has got the A, B, C and D matrices, which have values and which have been directly obtained through the math script node. Now you'll notice that if I just feed these values in here into the controls I had created for my state space representation in the beginning, I will be able to obtain the state space equation. So I'm just going to fill them in and show you how this works. So I've filled them in and I'm just going to run this now. I'm just going to expand this indicator so that it's easily visible, and there we are. We have our state equations right there. So it's as simple as that. You just drop the right VI onto your block diagram, create controls, fill in the values, and you'll have your state representation. Now moving on to the other representations that we have, I'm going to show you some more. So here we have the zero pole gain model. So all that is done here is that we just tell our system where the poles are located and where the zeros are located, and it will obtain the system representation just from that information. Again, we need to draw the system representation in order for us to be able to see it. So I'm going to use this zero pole gain draw equation here, connect it to my system and add an indicator here. And just to have this data together, I'm going to pull this down here next to the zeros. I'm going to pull down this indicator next to my poles, and I'm just going to fill in some information here which we always typically would arrive at. Let's say I have 1 0 at -2, and let's say I have another 0 at 1, and let's say my poles are at 1 plus I, and the complex conjugate would be 1 minus I. So I'm just going to type that in here. I'm going to run my program, and there we have our equation, which is obtained from the pole zero model. This is as simple as that. There's nothing more complex than just dropping the right VI on the block diagram and getting it all done from there. Now there's another method in which we can have our system, which is called the PID model. So basically what this system does is that it takes inputs in terms of the integral time, the proportional gain, and the derivative time, which you would typically have if you're generating a PID controller. And based on that, it would give us the transfer function. So I'm just going to add controls for all three quantities. You see they appear here, and I can fill them in. And I'm going to, because this gives a transfer function output, I'm going to have to use the draw transfer function VI here. And I'm just going to create an indicator here. It's gone all the way up, so I'm just going to pull it down right here. Now, just for simplicity's sake, I'm going to enter 1 as values for all three parameters, and I'm going to run this. And there's our equation, which has been obtained from the PID model. So this is basically just various ways, according to what you've decided to model your system in, according to what you're comfortable in. You could use any one of these methods that I've shown you: the transfer function, the state space, the math script, pole zero, or the PID. Now that we have this, there's one more thing, one more way in which we can have our model, which is the interactive design model. And I'll just come back to that a little bit later after we've gone through the next part of the webcast here. So now that we already know what our system looks like, I want to be able to find out what the behavior of my system is like. So I'm just going to move on to my time analysis and later to my frequency analysis. My time response and my frequency response, namely. So for that sake, I'm just going to use the first model that I have, because all this can be done on any of the models. So I'm just going to have my palette here again, my time response. Let's say I want to find the step response and the impulse response. I'm going to drop both these VIs on my block diagram. I'm just going to change the instance of this to a transfer function and an instance of this to transfer function as well. All I have to do is feed it my transfer function model, and similarly for this one as well. And I'll create indicators for my step response graph and for my impulse response graph. And it's as simple as that. So here is my step response graph, and here is my impulse response graph. I'm going to run the program. See that both my graphs appear. So it's very simple. You just pick up a VI which does what it's designed to do, which is what you want to do, and add an indicator, and that's done. Now that I have this, I might also want to find the parameters of my time response, such as overshoot and peak time. So I'm going to use this VI called the parametric time response data. I'm going to give this my transfer function as well, and I'm going to obtain my parameters through an indicator here. So this indicator will basically give us quantities such as rise time, peak value, settling time, overshoot percentage. So that's what we see, peak value 2. So you can use this to find out the various parameters of your system, and it's pretty handy for any controlled system designer. Now I'd like to move on to the frequency response, which is another thing which is very important in the design process, and you might want to view things and tweak around with your system and go back and find out how it behaves. So going to the frequency response palette, I'd like to show you basic things such as the Bode plot, for which I take the Bode VI and I just drop it onto my block diagram. I'm also going to show you the Nyquist plot, for which I take this Nyquist VI and drop it onto my block diagram. And I'm just going to feed these. I'm going to change the instances of this to transfer function so that I can give it a transfer function input. Like that. I'm just going to move these models back down because I'm done with them for the time being. And now I'm just going to create an indicator for the Bode magnitude as well as the Bode phase. These are my two graphs here. So as soon as I run the program, you'll see these graphs appearing. There we are. We have the Bode plots right in front of us. Now I'll add another indicator here for my Nyquist plot, and you'll see that that too appears really easily. Just going to run the program once more, and there we have our Nyquist plot. So it's as simple as that. And if you're interested in any of the dynamic characteristics, then we can go into the dynamic characteristic palette and say I want my root locus. So I take the root locus VI and drop it onto my block diagram. I want to see a pole zero map, so I take this VI, the pole zero map VI, and drop it onto my block diagram here. And again, I'm going to change the instances to transfer function. I'm going to give it an input for the transfer function model, and I'm going to have an indicator for my root locus graph, and similarly one more for my pole zero map. So my root locus will appear here, and this graph is just gone a little bit ahead, so I'm just going to pull it down, run this VI, and there we see both our graphs appear. Now depending on what your system is and what coefficients you've given, these graphs will change as they are supposed to. So for what I've given, this is what my root locus and pole zero map look like right now. That's the root locus and that's my pole zero map. So it's really simple, and you can use all these VIs to find out more about what your system does and how it behaves. Now let's go and explore some of the other things that this palette has to offer. So we have another set of VIs called the model interconnection, which is here. The model interconnection palette basically helps us to combine systems. If you have two different transfer functions, two different components of a control system, and if you want an equivalent representation or a transfer function, you can use these VIs. So if you have two systems in parallel, you can use this VI here, the CD parallel VI. If you have them in series, you can use this VI here. If they're in feedback loop, then this is what you use. And there are various different options available for you to connect. Now if you want to convert your model from, say, the state representation to a transfer function model, then you can use something like this, which is in the model conversion palette. So you just have to choose whichever VI here depending on what you want as your result, and you can just give it the input of any other form and it will convert it readily for you. So this also comes really handy, say if you have a transfer function and you want to know the elements of the ABCD matrices. Now there's another set of VIs here called the model reduction VIs. So what this does is it will do a pole zero cancellation if at all possible, and it will reduce the number of states in the system for us. There's also a predictive control set of VIs here which can implement things like Kalman filtering, and it will basically help the user build complex control systems easily. And finally, I'm going to come to the thing that I had left out earlier, which is the interactive design method of designing your control system. So this is what the VI looks like. It's in the interactive design palette. I'm just going to drop it onto my block diagram. So this basically, if you notice, it looks similar to the other regular Express VIs that you have, besides the fact that it's not blue, but it's slightly pink or brown. So what this does is that it gives out a control system in completion, and you can interactively tweak the parameters to your satisfaction and get to know how the system will behave before you actually generate the system. That is the advantage. So here you see it says controller out. So if you just create a little indicator here and you go down, then this is where you will actually see the parameters of the controller that you're generating. So I'm just going to run this program and show you what we can do with this. So as soon as you run this, a window pops up in which there are 4 tabs, as you see: configuration, synthesis, specifications, analysis. And you can specify almost everything for a system here. So in configuration, you can specify the control topology, the system topology. You can model an actuator, a sensor, and it will all come up there. And once this is done, you can go to the synthesis part. So here what we're doing is you can choose your controller type, if you want PID, a filter, a lead lag, and depending on what you choose, what you see on top will vary. And what you see on top are basically the performance characteristics. So you can tweak the settings here, and effectively you can see that things here will change. So I'm just going to change the gain here, and you see that my Bode diagram and the location of my poles are changing. So if you know that you want your poles in a certain way, or you want your Bode diagram to look in a particular way, then you can just tweak these until you reach that stage, and then you can go on to the next stage. So then let's come to the specifications here. If you have certain requirements like a particular maximum overshoot or a particular settling time, then this is where you can play around with the settings and see whether your Bode diagrams and your the pole diagrams actually represent that performance or not. And it will also give you a range. You'll see that there's a red and a green LED here to tell you whether your system is within the parameters that you've specified or not. So you can do a step response. You can also specify things such as the maximum damping ratio, the maximum natural frequency, and you can see how the system behaves when you specify certain things. Now finally, coming to the analysis, this gives you 4 graphs that you can look at, and you can specify what you want in all 4 plots. So they correspond to these 4 tabs here, and you can choose what kind of response you want, whether you want to see the impulse response or the Nyquist plot or the step response. You can choose the same for all the 4 tabs, and that's how you'll be able to find out and basically learn about your system, what's happening and how it's behaving. And once you're satisfied with everything that you've configured here, you just have to press OK, and it will basically generate a system for you at the output. And that's how it works. So this is how the interactive design VI for control systems is very intuitive and very user friendly, and you can very easily just drop one VI on your block diagram, run the VI, fill in all your specifications, and be done with the exact controller that you want. Now another thing that finally you need to do once you finish designing, simulating, and verifying your control system is implementation. So I'm going to take you to the implementation palette, which is here. And you can either choose to do it through a discrete transfer function, a discrete pole zero gain, or a discrete state space representation. So let's just say I want a discrete transfer function. So I pick up that PI and I just drop it on my block diagram. Now when all I have to do is, when I click on this, I'm going to specify whether I want a multiple input, multiple output system or a single input, single output system. And here is where I can see a preview of what my system is. Here is where I can specify the coefficients for my numerator and denominator depending on what kind of a system I want, depending on what I have learned through the past 4 processes of design, simulation and verification. And sometimes what happens is you might already have a model saved, a particular control system model. Like for example, I just showed you 4 or 5 days of creating a model in LabVIEW. So once you've created that, you can actually save it. And then once it's saved, you can load the model from here directly, depending on whatever you want. And that will automatically appear here, and you'll be using that model to actually come up with a implementable discrete transfer function. So once that is done, it can be deployed to hardware in the coming stages. So this brings us to the end of this week's content for this webcast. So I have a couple of interesting things for you to follow, and just going to take you through to the final stages. So this is what we've seen till now, and let's go to contest of the week. So the contest is going to be live now soon in the next 10 minutes, and I'm just going to show you the contest question right here, and it'll be up on the website for you in a while to solve. So this is the contest. You have a system that consists of a tank containing a liquid and an inlet to its tank, and the flow through the inlet is controlled by a valve. The liquid level is sensed and used by a controller to control the valve. This is the scenario. Now what you need to do is make and state the necessary assumptions. Be logical and just assume whatever you require by the real behavior of the system, and model the system and perform analysis on the system to attain the overall transfer function, the state space and pole zero representations, the Nyquist and Bode plots, the overshoot settling time and peak value. What you need to keep in mind is that if I decide the parameters of my system are going to change, these quantities should also change. So this is what the contest of the week is. Now for learning and extended participation, I encourage you to log on to LabViewEnabled.in and stay up to date with all our Webcast Wednesday activities, and you can get all your queries solved in the sessions. You can also interact with your peers and industry experts. You can participate in these weekly contests and win up to 50% discount in CLAD and other National Instruments certification examinations. Attend 20 webcast sessions and win a free CLAD attempt. This is something you should keep in mind. So watch the recording of this session and participate in the contest of the week. So we have a upcoming webinar on LabVIEW and data acquisition, which is on September 26th. This webinar will give you a complete insight into NI's graphical system design platform and how it enables you to quickly design, prototype and deploy data acquisition, embedded control and test systems. So it's on the 26th of September 2013 from 2:30 p.m. to 4:30 p.m. Indian Standard Time. The venue, it's online, it's from your desktop or laptop. If you wish to attend this webinar, please indicate your choice on the online form which will follow this. So just select yes, please register me if you are interested here. So we'll give you a couple of seconds more to fill in your opinion here. If you have any doubts on the session that we just had or something else connected to this topic, you can start asking our consultants questions. So we're going to close the poll now. Okay. Thank you for attending this week's session of you again next week, and we hope to have a lot of replies from you for the contest. Stay focused, keep lab viewing. Good luck.